it's a great pleasure for me to introduce my dear colleague, Wanying Kang, from MIT, that's going to talk about her very interesting work regarding Enceladus and its thermohaline dynamics. In this regard, let me just introduce to you who is Dr. Kang. Dr. Kang holds a PhD in applied mathematics from Harvard University, and now she's working at EAPS, the Earth, Atmospheric, and Planetary Science Department from MIT under Professor John Marshall and Professor Sarah Seeger. She has lots of interests in building good understanding of the atmospheric and oceanic dynamics, not only on Earth, but also on other planetary bodies, taking numerical simulation as a vehicle and find potentially observable consequences through the collaborations with all other groups from astronomy and other sciences, astrophysics, and so forth from MIT. So today, she's going to talk to us about this very interesting work that she has been doing. And I had the chance to watch it through a common group of research that we work at MIT. And she's going to talk from now on. I'll pass the baton to her. And Dr. Kang, it's a very, very great opportunity for us to learn about your work, and we are very much looking forward to hear your talk. Please.
Thank you so much for the kind words and the introduction. It is such a great pleasure to be here and to be able to present to this very diverse group of people working on all sorts of different things that I don't know anything about. And I hope that by the end of this presentation, people will start to get interested in these icy moons and planetary science related topics. And potentially, if you're interested, I will be very happy to interact more afterwards. So now let me share my screen. Okay. Share screen. All right. All right. So I'm gonna present now. So Ilsen, could you confirm that you can see the screen? All right. If you can confirm that, I will just proceed.
You can go away. Everything's okay. Yeah.
Okay, everything's okay. Great. So hello everyone. Today, my presentation will be about the ice and ocean dynamics on Enceladus. So this work is I started working on this project since about 2 years ago in the GFT summer school with Glenn Farrell. And by that time, we were interested in why Enceladus have a very interesting ice shell geometry. And we tried to use some simple models and understand that. And then since afterwards, I joined MIT department as a postdoc fellow, working under John Marshall and Sarah Seeger, and we try to understand more about like the ocean dynamics part. And so what I'm talking about today is we'll have mainly can be divided into 3 parts. The first part will be focused on the ice shell, and the second part will be mostly about the ocean dynamics, and the third part is trying to understand how they interact with one another. Okay. So before I start, I would like to acknowledge my collaborators, John Marshall, Glenn Floral, and Suyash Bear and Tushar Mehta. We are all at MIT. All right, so Enceladus is one of the icy moons of Saturn. It was discovered in the 18th century, almost over 200 years ago. However, until the Voyager mission came along, not too much is known about this icy moon, except that it exists and it is surrounding Saturn. And then the Voyager took the mission to explore the outer solar system and trying to find trying to find the most interesting phenomena and find the targets that we want to study more in the next decades. And what comes along is Enceladus. It is very interesting. Azimuth locates right at the center of E ring. The E ring is basically made of a whole bunch of isolates surrounding Saturn. And by that time, the existence of E ring is still a mystery. And people don't know why it's there, because according to the orbital calculation, it cannot be self-sustainable. And people can try to, by that time, people start to make all sorts of guesses about Y forms. And one of the hypotheses is the E ring is actually made of ejecta from Enceladus. And that hypothesis is confirmed to be is exactly the right answer by the recent Cassini mission. But when Cassini mission is orbiting around Saturn and Enceladus, it has managed to take a very high resolution pictures of this very small icy moon that is only 250 kilometers in radius. And what is found is that although this moon is super small, it remains very geologically active. And over the South Pole, there's these geysers called, we call it tiger stripe, aligned with one another around 35 to 35 kilometers wide. And from these geysers ejecting water vapor along with a cocktail of different materials, including carbon dioxide, methane, and other simple and complex organic molecules, even including the amino acids. So that finding makes the Enceladus a very interesting object to search for extraterrestrial life. And what is even more surprising to find is that when Cassini is trying to take pictures of this icy moon surface, it finds that the surface is wobbling about its rotating axis. So this libration motion is a kind of mystery because it cannot exist except the ice shell is completely decoupled from the core, the silicate core underneath. And that means there's a global subsurface ocean underneath the Enceladus ice shell. So what keeps these small icy satellites so active is the answer is actually tide. So over time, the Enceladus and another icy moon of Saturn called Dione, they start to resonate, and as a result, both of them undergo their orbits become slightly eccentric instead of perfectly instead of orbiting Saturn in a perfectly circular orbit, the Enceladus sometimes is a little bit farther away than other times from the host Saturn. And that means the tidal forcing, which tends to stretch the moon along the tidal axis. So tidal axis is the line between the Saturn, the host, and the satellite. So try to stretch the icy satellite along the axis. That force the amplitude of that force will vary with time. Sometimes it's closer. When it's closer, the forcing is very strong, and when it's farther away, the forcing is weaker. And these time-varying tidal forcing constantly deform the ice shell and the silicate core underneath. And that will induce tidal deformation over time. And in a viscoelastic media, when you're deforming the system, you produce heat. And if you do the calculation using some thin ice model and trying to calculate the deformation, horizontal vertical deformation of a spherical ice shell under this type of tidal forcing, you will find that tidal heating actually amplifies over the two poles and have a minimum value over the equator. And since that the tidal heating is polar amplified, so it's not surprising to us that the Enceladus ice shell is slightly thinner over the polar regions. So by taking measurement of the size, the mass, and the gravity, the momentum of inertial liberation, combining all these measurements, people were able to reconstruct the ice shell geometry pretty well for Enceladus. And what people find is that the polar regions have much thinner ice shell than the equatorial regions. And over the equator, the ice shell is almost as thick as 30 kilometers, and the polar region is about 10 kilometers. But what is surprise to us is that besides this powered thinning pattern, there's a very strong hemispheric asymmetry in the system. So the South Pole, where all the geysers are concentrated over, and the ice shell is much thinner than the northern hemisphere, and it's only on average the South Pole is only 6 kilometers thick, and and over the geysers is completely melted, and is allowing constant mass exchange between the subsurface ocean and outer space. So this asymmetry is unexpected because Enceladus orbits have almost zero obliquity, which means the rotating axis is perpendicular to the orbital plane all the time. So then the tidal forcing is expected to be perfectly symmetric between the two hemispheres. So then why the ice shell is not symmetric between the two hemispheres is a long-term mystery. So that leads to the first topic I would like to talk about today, which is why Enceladus have such an asymmetric ice shell. So before I start to talk about our hypothesis, I would like to review some previous work. So in the past, the people have been trying to come up with some mechanism to explain the unexpected asymmetry, both for the ice shell geometry, but before people know the ice geometry that well, why all the gases are concentrated in one of the poles. And one hypothesis is proposed by Adam Schulman in 2013, and they find that if you simulate the ice convection, 3D ice convection, and with the bottom heating, what you will find is that if you have a little topography bump in the silicate core, the convection tends to be much better organized than the convection system with a perfectly spherical core. So shown here is the 3D 230K isosurface, and you can see when the core is perfectly spherical, the perturbation is kind of random, and when there's a topography bump over the South Pole, then the convection and also the heat flux tends to be more concentrated. And Schulman wants to propose that this concentrated convection can explain the gas formation on Enceladus. There's and besides this, recently people start to think about the potential impact, the giant impacts. So if probably a long time ago, the Enceladus has been hit by a meteorite, and they have tested the different meteorite size and velocity, and what they find is that these giant impacts can possibly penetrate the 20-kilometer thick ice shell and fracture it. And over time, probably this fracture will be reorientated to the South Polar region through the true polar wonder. And there's and if you look at the geometry and the ice geometry, there seems to be some pattern that indicates the true polar wonder has happened in the past. So although these theories that I just introduced were able to explain the existence of the asymmetry and the South Polar terrain geysers, however, it requires some luck for for Enceladus to end up in such a strange configuration, it have to be heated only for one time in the past, not too many, it's not zero, it's not too many, but just once. And there's plenty of time and the reason mechanism to reorientate the fracture terrain towards the right location. So to leave this requirement, Hemingway et al. 2019 have proposed a slightly different mechanism, where they where they say, okay, the reason why Enceladus have a very asymmetric ash shell is because the Enceladus undergoes a secular freezing. So I believe everybody have the experience to put a beer into the to the freezer, and overnight when you take it out, you find that the beer has already exploded, and that is because when the water freezes, the volume will expand, and that will in confined volume, in a confined container, it will create overpressure, and that overpressure will tend to only be released from one spot, and that spot is likely to be the weakest spot. Since that since that the tidal heating is likely to be amplified over the polar regions, then one of the poles will be the most vulnerable place. And once the pressure got released from that one single pole, then and there's no overpressure anymore, and the eruption won't happen on the other side of the planet. And that is why there's only one pole that have very thin ice shell and have all the geysers located there. So, but since that this so although this theory sounds very nice, it still requires a secular freezing. So Glenn and myself, when we look at this problem, we want to find a mechanism that can explain this phenomena without any strong requirement for either the history or the history, the evolution, or the of this azimuth. So what we try to propose is that this dichotomy can automatically arise by itself through an unstable mode, through the growth of an unstable mode that is embedded in the basic ice dynamics. So in order for this to work, we need two key elements in the mechanism. So first of all, we need a positive feedback that can amplify the pre-existing ice topography, which means that this feedback needs to be able to thin the regions where the ice is already thin and thicken the regions where the ice is already thick. And we will talk about what will be the candidate to provide this sort of positive feedback later. However, if you only have positive feedback, it's not enough, because if all the wave numbers, the small scale, large scale, all different wave numbers are growing at the same rate, then we will end up with a super patchy icy ball instead of having instead of what we observe now, that all the gases and everything is concentrated in one of the poles. So what we need is a scale selection that can surprise all the small scale anomalies and leave the large scale anomalies alone. And we will, to demonstrate that this can indeed happen on Enceladus, we use a conceptual model. So I won't go to all the details, but I will just briefly overview what's the processes that we consider in this system. So the first process that we consider is the heat loss to space. So we know that the surface is cold around the 60 degree Kelvin, or minus 110 degrees Celsius, super cold. And that temperature is set by relative equilibrium. And underneath, at the water ice interface, the temperature should be much higher, should be 0 Celsius or 273 Kelvin. And this huge vertical temperature gradient will induce a heat flux pointing outward into the space, and that will transmit the heat from the interior to the outer space. So we can estimate this heat flux using a one-dimensional heat conduction model. And since that we know the heat conductivity is a function of temperature, after we count for all these things, we can solve for the equilibrium temperature profile and then the heat flux. And this heat flux will be amplified over the regions where the ice shell is thin, because intuitively thin ice is cannot insulate the system as well as the thick ice, and therefore the heat loss should be faster over there. This will sorry. So this process will tend to suppress all the thickness anomalies, because thin ice lost heat more efficiently and therefore it tends to grow back. So the second process that we consider is the tidal heating generated in the ice shell. And we suppose that this heat will be the major heat source that is balancing the heat loss into the space. And we take a thin ice model that is proposed by Bills in his series of papers in the 2016, 18, and 19. We use this model to calculate the deformation, the horizontal and vertical deformation of the ice shell under the tidal forcing. And then from that, we can calculate the dissipation rate due to different different modes. And from that, we find that if the ice is completely flat, 20 kilometers everywhere, then the heat production will be amplified over the polar regions. However, we have to have a way to compensate to account for the rheology effect when the ice shell have a varying thickness. So the rheology effect is that when your ice shell is thin in some region, then it tends to produce more heat in that region. And you can understand this feedback intuitively by considering a rubber band. So if you create a weak point on the rubber band, and then you stretch it, then you expect most of the heat will be produced in the region around near the weak point. And the same thing can happen on Enceladus. If some region, South Pole, North Pole, equator, wherever it is, if the ice is thin, then under the same amount of tidal forcing, it will tend to deform more and dissipate more. So this parameter will P alpha will be introduced when we will multiply this H over H0. H0 is the mean ice thickness. So we will multiply this factor to the membrane mode, and that will be able to account for this ice rheology feedback and make the thin ice dissipate more efficiently. This tidal heating, this rheology feedback will be able to provide the positive feedback that we need for topography to grow. So thin ice will tend to produce more heat and gets even thinner. Okay, so now that we imagine there's some ice topography developed in the system, then the ice flow will kick in and transport the ice from the thick ice regions to the thin ice region. So since that the polar region produce more heat, then the ice flow will be powered. And we can use downward ice sheet model to estimate this process. And substituting the correct boundary condition, we can solve for the mass transport induced by the pressure gradient at the surface. And this process will tend to smooth out, it almost behaves like diffusion. So therefore, the small scale thickness variations will be removed more efficiently than the large scale thickness variations. Okay, so now let's put everything together, all these three major process in the ice shell model, and integrate the model forward, starting from a perfectly uniform ice shell. And over time, we will reach equilibrium, which is shown by the black solid curve in this figure, with axis on the left. So what we find is that the polar regions is thinner than the equatorial region. That is expected because tidal heating is polar amplified. And then what we can do here is that we can try to do a stability analysis to this system. We can linearize all these terms around this equilibrium state and get a matrix and try to ask is there any unstable mode? And we find that there is one unstable mode, and this unstable mode has structure that is tilted from one hemisphere to the other hemisphere. So if this mode can grow, then we will start to develop some hemispheric asymmetry, and eventually probably one of the poles will be completely melted, as we observed. So here we start, instead of starting from a perfectly flat ice shell, we start the initial condition, we introduce some tiny irregularity in the initial condition. What we find is that over time, as you can see, the south pole here start to get thinner and thinner, and eventually it stabilized and as some super shallow. Sorry, I try to fix it. So let's get to the end of the simulation. By 10 million years, the south pole is almost completely melted, while the north pole still have a pretty significant amount of ice, around 15 kilometers. So we can do the same exercise using a 2D in a 2D map. And before we ignore the zonal variations, and here since that the tidal heating have a minimum value under the subsatin and anti-satin point, the equilibrium ice shell geometry is thickest in these two spots at 0 degree and 180 degree longitude. And if we compare this this ice geometry profile with the observed ice geometry profile on the right, we find that it captures a lot of features that we see, which include this bomb near the anti-satin subsatin point, and some minimum value and some general, and of course the general structure that is the polar thinning structure and the asymmetry. Okay, so does this symmetry breaking always happening? If that is true, then we expect all the icy moons to have asymmetric ice shell, but that is not what we find. In fact, the asymmetry can only happen in a specific parameter regime. So here I explore two key parameters. One is the surface temperature, which sets the ice viscosity. Basically, it determines how hard ice is it to deform the ice shell. And then the other parameter that we look at, that we examine, is the mean ice thickness, and that determines. So since that the system is in a heat equilibrium, so that this parameter sets how much heat is produced in the system. So this exploring these two, all these different combinations, we find that if the ice shell is too thick and the temperature is too high, then it's eventually we will end up have a polar thinning ice shell that is symmetric. And to the other side of the diagram, the two polar regions will be both completely melted. And only in somewhere in between, the symmetry breaking could happen. So according to our current understanding of Enceladus, it have around the ice shell thickness is around 23 kilometer, and the surface temperature is around 60 to 80. So it falls right in the symmetry breaking permitting regime. And this symmetry breaking regime, actually, if you make some simplification of the idealized model that we used, we can try to predict this asymmetry breaking regime analytically. And here I won't go to all the details. So this where this asymmetry breaking could happen actually have to do with the time scale of a heat conduction, tidal heating, and ice flow. So using these time scales, we can estimate using this threshold to predict whether symmetry breaking will occur or not. So it seems that now we understand what's going on in Enceladus, but can we try to apply this model to a genetic azimuth in the solar system? And the answer is is a little bit disappointed. The answer is no, because there are certainly Enceladus is not the only one icy satellite that falls into the symmetry breaking regime, but we don't find other planets to have this very interesting behavior happening on them. And one example that we know about is Europa. So why? So Europa have a actual thickness of around 15 kilometer, and the temperature, surface temperature is around 110 Kelvin. It falls right in the symmetry breaking regime. However, its astral turns out to be perfectly symmetric. So why is that? It has to do with the ocean dynamics. So in reality, the ocean and ice forms a closely coupled system. So instead of, but that interaction with the ocean is completely ignored in the model that we just talked about. What would really happen is that the ice gel will impose heat and salinity flux onto the ocean from top, and that will drive ocean circulation. And then the ocean circulation will redistribute the heat, transport the heat around, and then induce melting and freezing in the ice gel, and that will reshape the ice geometry. And that coupling is missing. And and that leads to the second part of our of my talk, which is the ocean circulation and heat transport on Enceladus. So to understand the ocean circulation and the heat transport, it's crucial that we know the boundary conditions. So from the top, the ice shell ice shell thickness is varying with latitude and longitude, and that by itself will provide a strong forcing. So why is that? Since that the equatorial region is thicker than the polar regions, there will be an ice flow transporting ice from the equator to the poles. And in order to sustain such this thickness gradient, the equatorial region have to be freezing and the polar regions have to be melting. Using the ice flow model, we can estimate the required freezing and melting rate in order to compensate the ice flow transport. And this will this will induce salinity flux into the ocean, and that will make the equatorial water to be slightly denser than the polar water. And on top of that, there's also the ice shell also impose a heat flux into the ocean. So why is that? The freezing point is a function of pressure. And since that the water-ice interface always have the temperature of a freezing point, the polar regions will be tend to be slightly warmer than the equatorial region. And that temperature difference could be as high as 0.1 degree. You may think that this 0.1 degree is tiny, but that is based on our experience dealing with Earth's ocean. For icy satellites like Enceladus, 0.1 degree is huge, because if you have this the 40 milliwatts of heat coming from below, and this 40 milliwatts is what required to balance the total heat loss of the system. If you put these 40 milliwatts from bottom, the temperature gradient developed vertically will be only 10 millikelvin or even less. So this meridional temperature gradient is very large, and that will also drive a circulation. from a top. Okay. However, so besides the upper the heat flux and the salinity flux from the ice gel, there will be also heat flux coming from below. However, this boundary condition remains under debate. We don't know how much heat is produced in the ice gel and how much is produced in the silicate core. So here we're gonna consider these two different scenarios. And in fact, whether the heat is coming from above or below will make a huge difference in the ocean circulation and heat tracer transport on Enceladus. If the heat is coming from below, we will expect the convection to take over, and that will the dynamics will be somewhat like what I show here on the right bottom. So the middle the left panel is more relevant for the Enceladus because it's a fast rotator, and we will expect some convection plumes to shoot from bottom to the ice gel along the rotating axis. However, if most of the heat is produced in the ice gel instead, then we would expect the overturning circulation to take over, and the ocean may be more stably stratified, and the convection that is shown on the right may not show up. So there, and on top of this, there's another level of complexity, and that is associated with the ocean salinity. We don't know how salty the ocean is, although we collect the samples from the South Pole, but most of them are completely fresh, and the few ones that is salty give a very poor constraint on the ocean salinity underneath the ice gel. So and the ocean salinity make a huge difference on the equation of state. If the ocean is very fresh, as shown by the blue curve, the water density will increase with temperature, meaning that it will contract upon warming. Sorry, wrong order. Will contract upon warming, as and that is a so-called anomalous expansion. Whereas when the water is very salty, then the opposite tends to happen. Water will expand upon warming, as normal material will do, and that will by having different salinity, the ocean equation of state will change, and that changes the way that density respond to the temperature anomalies. However, the constraint so far on the Enceladus ocean salinity is still very poor. So therefore, it's crucial for us to understand how the salinity will affect the ocean dynamics, and whether we can use the ocean dynamics to put a constraint back onto the salinity. So what we're trying to figure out is really to find where Enceladus is in this two-dimensional parameter space. So the y-axis is the heat partition between the silicate core and the ice gel, and in the x-axis is the ocean salinity. And we expect the convection to happen when the ocean is salty, when water expands upon warming, and when there's some heating coming from the core. And in the regime where anomalous expansion take over governs, we expect the salinity-related process to dominate. And there could be convection driven by freezing from a top, and there could be overturning circulation induced by the salinity and temperature gradient. So now, in order to understand this process, we take a zonally symmetric non-hydrostatic GCM. This model is configured based on the MIT GCM, and we use the realistic ice geometry. We relax the upper surface and temperature at upper surface temperature to the local freezing point, which is varying with the pressure. As shown here, the equatorial region is slightly colder than the polar regions. And then we also impose a freezing melting rate from a top, and that freezing melting rate is derived from an ice flow, the ice flow model. So under this forcing, we find that temperature, the system start to develop temperature and salinity gradient as you expected. The polar region is warmer, and the equatorial than the equatorial region, and it's also fresher than the equatorial region. So it's so both of the temperature and salinity variation will induce a density gradient and drive circulation. So there's no ambiguity about how salinity can affect the density. Salty water is always denser than the fresh water. However, for temperatures have this ambiguity because different salinities, water has different salinities respond to temperature in different way. When the ocean is salty, cold water is dense. But when the ocean is fresh at 4 PSU and 10 PSU, the polar water, the warm water over the polar regions is denser than the equatorial water. And adding these two effects together, we got this density profiles shown on the bottom panels. So when the ocean is salty, dense water located at the equator, and therefore we expect convection to happen there. And when the ocean is very fresh, the dense water located over the polar regions instead. Somewhere in between, the density variation cancel out. The temperature-induced and salinity-induced the temperature gradient cancel out with one another, leading to a weak density gradient. But then we can try to see what kind of circulation is driven by this density variation. So in this salty scenario, since the equatorial water is dense, water tends to sink from the equator and rise over the polar regions. And in the fresh fresh regime, where water is dense over the polar regions, the opposite happens. And somewhere in between, the circulation is weak, then is about 1 orders magnitude weaker than the two end members. And no matter how this circulation how oceans, in which direction the ocean circulates, whether it's sinking over the poles or the equator, the heat is transmitted from the polar regions to the equatorial regions as the warm water is mixed toward equatorward and cold equatorial water is mixed poleward. And that can be seen from this bottom panel. Shown here is the meridional heat transport. Northward is positive, southward is negative. And as you can see, these three scenarios, they all have powered, and they all have equatorward heat convergence. And this heat, and since that the heat and the circulation is much stronger, when the overturning circulation is strong, and the heat transport is strong in the end member scenarios than the scenario with intermediate salinity. And this heat transport have to be transmitted towards the ice shell. And therefore, the equatorial in the equatorial region, heat is transmitted from the ocean to the ice, and over the polar regions, the opposite is happening. So now we can start to consider the heat budget. So we have this conductive heat loss through the ice shell, and that can be calculated from the conductive the one-dimensional heat conduction model. And this heat conductive loss rate is higher over the polar regions than the equatorial regions. And we have this ocean ice heat exchange, H ocean, and on top of that we have the latent heating absorption and release due to the freezing and melting. And adding all this together, since that the system have to be in the heat budget balance, the tidal heating have to be able to compensate the net heat gain and the heat loss associated with all the other process. So shown here in the solid curves are the required tidal heating in order for this system to be in a thermal equilibrium state. And shown on the black dash curve is the predicted tidal heating from some tidal dissipation model. By comparing these two, you can see that when the ocean is in some intermediate salinity region, have an intermediate salinity, and the predicted tidal heating matches much better with the predicted tidal heating from the ice dissipation model, and we can measure the mismatch between the predicted and required tidal heating using using their standard deviation. So that mismatch index is shown in the right panel. As you can see, the mismatch index decreases and the increases with salinity with a minimum around 10 to 15 PSU. We can do the same exercise for the heat from below scenario. And since that in this scenario, all the heat production is assumed to be happening in the silicate core, there's no heat production in the ice gel by assumption. And therefore, we should really compare these solid curves with this zero line here. And since there's no tidal heat production in this in ice, there's no process that can compensate the equatorward heat convergence and the fast heat loss over the polar regions, and that leads to overall much higher mismatch index for the bottom heating scenario. And therefore, so by trying to understand the ocean circulation heat transport on Enceladus, we can say something about the undersurface ocean salinity and heat partition. So it's unlike, since that we need some process, the polar amplified heat production to compensate the equatorward heat convergence and all the other processes, we need the shell heating to dominate, and also the ocean salinity is unlikely to be super high and super low, should be in some intermediate range, because otherwise the equatorward heat convergence will be too strong to be in balance with all the other processes. So now that we understand the ocean dynamics and heat transport on Enceladus, we can start to try to couple this ocean model with the ice hand by hand, and try to understand how the ice evolve over time, and under the influence of this ocean ice coupling. And in particular, we would like to understand why the symmetry breaking happens on Enceladus but doesn't happen on Europa. So here is the ice evolution model, where I couple the ocean model that we just used with an ice evolution model. We need, in order to integrate this system to over millions of over a timescale of millions of years, we multiply a factor to the ice evolution processes and to accelerate the change of ice shell geometry. And by the end of so we start and we run this ice evolution model for using Enceladus parameter and Europa parameters, and starting from the same initial ice geometry. And that initial geometry is shown by these grid curves on these two panels. After integral this model for millions of years, we find that Enceladus using Enceladus, the Enceladus parameter leads to a symmetry breaking between the two hemispheres. The south pole is completely melted, and the north pole is not. And also over time, the equator to pole ice shell thickness gradient increases. However, on Europa, the opposite happens. So the two poles now are all freezing over time, and the equatorial region is melting, and eventually the ice shell becomes much flatter than the initial profile that we feed into the model. So why Why this doesn't happen? So the simple answer is that Europa is too big. So what will happen when if the planet, if icy moon is very large in size? So if let's imagine that the equator, initially there is some equator to pole ice thickness gradient, and this and also the moon is very large as what it is in for Europa. So what's going to happen is that the anomalous expansion is completely suppressed by high pressure. And therefore, there will be no way for temperature and salinity to cancel one another when they try to drive the overturning circulation. And that will generally lead to a stronger overturning circulation and a stronger heat transport as a result. And secondly, since that the moon is larger in size, the gravity will tend to be stronger as well. And therefore, under the same if the equator and equator to pole density variation is the same, the circulation tends to be stronger because the gravity is much stronger. And then on top of that, the equator to pole temperature gradient underneath the same underneath the ice shell will be much larger because the temperature, the freezing point and variation is proportional to the pressure changes. And the pressure, and since that the larger moon have a stronger gravity, the same amount of ice thickness variation will lead to a greater pressure difference, and therefore a stronger temperature variation. So if you account for all these processes together by using some energetic argument, we can come up with these scaling laws that the meridional stream function should be proportional to a squared. A is the radius of the icy moon, and the meridional heat transport hy should be proportional to the a cube. So we can examine this scaling law using numerical models, and we find that it matches very well, and we consider different scenarios, we consider different salinities and heat partition. They doesn't make too much of a difference. And we also have this conceptual model that can try to, where we try to account for the subtle differences between the 4 different scenarios we consider here, and they matches with the numerical model reasonably well as well. So now that we know Europa, since that Europa have a much larger size, it must have more heat to transport it powered, if under the same amount of under the same ice geometry. So now the question is what is we need to solve an inverse problem, trying to understand how much the pole ice thickness gradient will develop if the moon gets larger. So in order to understand that, we have to have another scaling law tells us how the heat transport depends on the equator to pole ice thickness gradient. And that is so after some simple calculation, we find that the heat transport should be proportional to delta H squared. Delta H is the equator to pole thickness difference. And if we assume that the system is in a heat budget balance, so we consider this ice rheology feedback and the heat conduction is more, and the fact that the heat conduction is more efficient over the polar regions. So if you solve this system, the heat balance system, we find that the equator to pole ice thickness variation should be inversely proportional to the radius of the moon to inverse. And that when we derive this formula, we fix the bulk density, salinity, and equation of state. And if you account for that, that will make the Europa that will make the Europa to have an even flatter ice shell than what is predicted by this theory. So since that Europa is 6 times as large as Enceladus, so therefore we expect the equator to pole thickness difference to be 6 times smaller. And if you account for all the other effects, the delta H on Europa is likely to be smaller than 1 kilometer. And that is why, basically why we don't expect any symmetry breaking to happen, because the overturning circulation on Europa is too strong, and the ice pump mechanism basically smooths the entire smooth the ice shell geometry out and make the ice shell to be completely flat. So to summarize, so today we talked about 3 small topics about the icy moons. The first one is about in the first one we try to understand the asymmetric Enceladus ice shell and find that ice rheology feedback and plus ice flow. We will be able to reproduce the asymmetric ice geometry we see in the observation. And in the second part, we study the ocean circulation and heat transport. We find that if Enceladus gonna be in a mass and heat balance, if it's gonna be in a heat balance, then it should have a lot of heat produced in the ice shell and should have an intermediate salinity. And third, which is the last part, we just talk about ice shell evolution. When we are trying to figure out ice shell evolution, size matters. The Europa, because the ice shell is the Europa is much larger than Enceladus, it's likely that Europa should have a much flatter ice shell, and the asymmetry is completely suppressed in Europa. So with this, I would like to thank you all for your attention, and I would like to take any questions that you have.